Hello and welcome to this video. In this video I will be talking about the acceptance rejection method. Okay, so imagine we have this goal. We wish to simulate x, a random variable, which we know have a known PDF f, but f is really hard to simulate from. We don't know any methods of simulating f. So instead, we only know a constant c and a PDF g, which is a PDF of some random variable y, such that f taken in x is less than or equal to c times g of x for all x in the sample space of x. So this is the sample space of x. Okay, now this might seem a bit incredible because it's actually quite simple, but this is all we need to generate random variables from the PDF f. Our algorithm looks like this. First of all, we generate y from g, then we accept and put x equal to y with probability f of x divided by c times g of x. And remember, f is less than or equal to c times g of x, so this will be between 0 and 1. And otherwise, we reject y and return to 1. To 1. And this is actually the whole method. So we generate from our proposal distribution, and then we accept it with this probability, this one here. Okay, now I want to remark something. Accepting with probability, with prob f of, oh, I'm sorry, it should have been like this, g of y. Let me just correct that. So it has to be for this y we just generated. Okay, so accepting with this probability is the same as accepting if u is less than or equal to f of y c times g of y, where u is standard uniform. I hope this is clear. So now I want to consider, why does this work? So I want to prove that y given u being less than or equal to f of y over c times g of y. This is my random variable that I put equal to x, because if this condition does not hold, I sample another y. I want to prove that this has the same distribution as x. And I'm sorry, there's a spelling mistake. I want to prove this is true. Okay, so I let B be a subset of the sample space of X, which is a subspace of the real numbers. Okay, now consider the probability of Y being in B given U is less than or equal to F of Y divided by C times G of Y. Well, I can use Bayes' rule to say that this is equal to the probability of y being in B and u being less than or equal to f of y over g of y times c. And then I have to divide by the probability of the event I condition on. So the probability of u being less than or equal to f of y divided by c g of y. And then I do something. I also add that y must be in the real numbers. This is free for me to add because this is always true. And since I then take the intersection with this event, then it is still equal to this, the probability of this event happening. Okay. Now, I use the law of total probability to rewrite these probabilities, because I can condition on y being equal to a small y and then multiply by the density of y. So I can write this as the integral over b of the probability of u being less than or equal to f of y g c g of y given y is equal to small y multiplied by g of y dy. And then similarly, this should have been r, sorry. Here I have that y just needs to be inside r, so here I integrate over r. And I have this probability, but when I said y equal to small y, I could just as well write small y in here. So probability u being less than or equal to f of y c g of y multiplied by g of y dy. Okay. Now I notice that u is uniform 0.1. So all of this will be equal to the integral of b. Then using the rewriting this in a similar fashion as this, I can use the CDF of u because I know that the right side here is between 0 and 1, and this is just the CDF taken in the right side. So this is equal to, So using the CDF of a standard uniform, I get that this is equal to f of y cg of y, and then still multiplying by this times g of y dy, and down here we have the exact same thing, just with over r instead, y cg of y gy dy. Now, a lot of things cancel out now. This cancels out with this, and this cancels out with this. Then these constants c we can bring outside the integrals, and then they will also cancel out. So this cancels out with this. So what we have left is the integral over b of f of y dy, integral over r f of y dy. But this is the density of x. So this is equal to the probability of x being inside b divided by the probability of x being inside r. But this down here is equal to 1 because x will always be inside r. So this is just equal to the probability of x being in b. So we have found that the probability of this y conditioned on u being less than or equal to this fraction has the same probability of being inside a set b as x. So this means that y given u less than or equal to f of y cg of y has the same distribution as x. And this is basically it. This is the entire proof that the acceptance-rejection method works. Now, how do we choose this C and G? This is not always clear. Sometimes you will have to use some trial and error, but generally you want your C to be small. I don't want to go further into that because it gets a bit complicated. I might do a follow-up video if anyone would be interested in this. But in some cases you can find the optimal C, but not always. Now, I want to do an example, which I will implement in Python in a moment. So my example, I have x is distributed with a PDF f, where f of x is equal to xe minus x for all x in the real line. And some of you might recognize this density, but let's imagine I don't recognize this density. This is in fact a gamma density. Or in this particular case, it's equal to E1 plus E2, where E1 and E2 are standard exponentials. But let's imagine we don't know that. We simply get this density from our bus, and we have to simulate from this density. Okay, then we might try to plot this density, and we might find, I will do that in a moment, And it will be clear that we can probably use some G, which is a exponential PDF. And that is exactly what I want to do now. So I have this is a program called idle. So my goal is to simulate with PDF equal to x times exponential function of minus x. I'm sorry about this system sounds. Okay, I will need a few things for this. I will need a package called numpy and a plotting package. Okay, so I first of all define my f of x as x multiplied by numpy exponential of minus x. Then I define g of x as, and now I have to make a choice. So let me just try to plot if I remember how to do this. So this gives me a vector of 100 points between 0 and 5. So now I can plot this, where I use these x's as my x values and f taken on x as my y values. And then hopefully this gives me a plot. Okay, so this is the density I wish to simulate from. I think I should be able to find an exponential, and let me just try and error a bit here. So if I try to make an exponential with rate a half, then this is the PDF of a proposal distribution is exponential rate 0.5. Let us see if this looks all right. So now my orange is my proposal. Well, I see that it is not above my f, but now I can probably find some constant if I just try to multiply this by, let's try 1.5. Well, yeah, it seems like my orange is above the blue line. So let's go with these settings. So my C is equal to 1.5, and my, let me just move this below, and my G of x is equal to the PDF of a exponential with rate 0.5, so 0.5 times the exponential taken in minus x times the rate 0.5. Okay, so now I can define my acceptance-rejection method, and I want n simulations. So first of all, I simulate y. And you can simulate exponentials using different methods, I will just use a built-in method. You could generate exponentials from uniforms using the left inverse method, which I have covered in another video, but for simplicity's sake, I will just use the built-in function. And one thing is that in the NumPy package, they use shape instead of rate for their exponentials. So this is 1 divided by the rate. So 1 divided by 0.5 or 2. And I just want a single simulation. So for I in range up to n, I want to do the following. While true, I want to generate a y. I want to generate a uniform. I think I do it like this. So I set the boundaries between 0 and 1, and then I want one simulation. Then I also want an output. I will use a NumPy array for my output. So if u is less than or equal to f of y divided by my c times 1.5 times g of y, then I accept my y. So I put x equal to NumPy append x comma y, and then I break. This will break the while loop. So the while loop will simulate a y, simulate a u, check this condition. If the condition holds, then it will accept y, and otherwise it will just start over from here. And I do this for every I in range 1 to n. So this will give me exactly n simulations. Now, hopefully this will work. So if I go down here, then I can simulate x as, let's just try 10,000 simulations. I will just add something here. If I is divisible by 100, then I want to print I. I don't know if this will be very slow or if it works, so I'll just make sure. Okay, so I simulate my x, then I create a histogram. I'll just try with 50 bins, and then I'll just draw the functions above it. That's fine. So let us try running this. What did it say? Positional argument follows keyword argument. Should it be like this? Exponential got an unexpected keyword argument shape. Wait, let me just try doing like this. Okay, it looks like it almost worked. Type error. Less than not supported between instances of non-type. Oh, I also would like to return my x. Okay, so this is my histogram. I can see that I have forgot to make this a density histogram. Okay, now let me just remove my proposal, and then let me expand this to, well, how far does this go? Around 8. So let me expand this to 10. And then let me consider. So the blue is my scaled observations. So you can see it's not an actual histogram, it's a density histogram. And the orange is the distribution I wanted to sample from. And as you can see, this, in my opinion, this looks great. So yeah, I guess that is it. I don't have anything to add. Yeah, so if you have any questions, you are welcome to ask them below in the comments. Or if you have any suggestions or anything else you would like me to know, please do write a comment. And otherwise, just have a nice day, and thank you for watching this video.